Hello students, good morning. Hope you all are fine. Today we are moving to a new chapter, that is moving charges and magnetism. This chapter is in the first part of your textbook, fourth lesson. Okay. So 4 more lessons are there in that chapter. Among that 4, first 2 chapters are purely related to magnetism. So when we say about magnetism, a bit of that you have studied in class 10, and in this chapter we are discussing how magnetism is produced because of moving charges. Then we are moving to different laws, theories, then rules. In 10th standard you have studied 2 or 3 rules, but here we are studying large number of rules which gives the direction of magnetic field in each case. Then finally a few more details in this chapter. Okay. Now today we will start with Oersted experiment. You all have studied Oersted experiment. What is the purpose of that experiment, or what is the conclusion from that Oersted experiment? Yes, Oersted discovered that a current carrying conductor is able to produce magnetism or magnetic field around it. A current carrying conductor will behave like a magnet. This was clearly explained with the help of Oersted experiment. Okay, so we will start now. That is, chapter is moving charges and magnetism. Our topic is Oersted experiment. So for this experiment, we need a current carrying conductor first of all. So XY, let XY be the current carrying conductor. Okay. This is straight wire. It can be of any wire, a conductor. It should be a conductor. Then it is connected to a battery and a key. Okay, this is the battery and this is the key. You know the direction of current is from positive terminal to negative terminal. So positive terminal, then current flows from X to Y. This is the first case, and like this. Okay. Now here he placed a compass needle near this current carrying straight wire XY. When he switched it on, current starts to flow through the wire and suddenly a deflection is noticed in the compass needle. Okay. So what does it indicate? When he switched on the key, current starts to flow through the conductor. You know, this compass needle is itself a magnet. If there is a deflection in the compass needle, it indicates that some sort of magnetic field or magnet is coming near it, isn't it? That is why deflection is caused there. So he concluded that this deflection is because the current carrying conductor is behaving like a magnet. This conductor is showing the property of a magnet. So he concluded that a current carrying conductor will behave like a magnet. Okay. So because of current, we can produce magnetic field. That was the first discovery made by Oersted. Starting from this discovery, we are moving to so many things. Okay. So here, this is the experiment and this is the conclusion. Now, here one thing we have to notice is, if the current flows from X to Y, to which direction is the deflection of the compass needle? If the current flows from Y to X, to which direction the deflection of compass needle? So for identifying the direction, or to study more about the direction, one rule was suggested, and that rule is Ampere's swimming rule. Ampere's swimming rule. Okay. So according to this rule, you can suppose the directions like N, north, then south, this is east, and this is west. And in this particular direction, when we compare this to the experiment here, you can see from north to south, current is flowing, right? And if it is flowing from north to south, to which direction does the deflection happens? Okay. So by Ampere's swimming rule, it is said that if a person is swimming in a direction such that, suppose this is the person. Okay. So he is swimming like this. Now, this is north and this is south. So he is swimming from where to where? From south to north. So from south to north, the person is swimming. Then you just look at his left hand. So this is the left hand, isn't it? This is the left hand. So the direction of the left hand will be the direction of deflection of the compass needle. Okay, that means towards the west, isn't it? Clear, no? Now this is N, S, so this will be east and this is west. So the direction of the left hand will give you the direction of the deflection of the compass needle. If I am reversing the direction in such a way that the movement is from north to south, okay, that is the person is like this. Okay, from north to south the person is swimming. Now look at his left side. What is the direction? If it is north, south, this will be east and this is west. Understood? So here the direction is, the deflection of the compass needle is towards east. Clear for you? So with the help of Ampere's swimming rule, we can denote or we can note the deflection of compass needle to which direction when it is placed near a current carrying conductor. So look here, if it is from X to Y, what is the direction of compass needle or direction of deflection of the compass needle? As if it is from X to Y means from north to south. So the deflection will be towards east, isn't it? So from north to south, deflection is seen that towards east, and from south to north, the deflection is towards west. So to keep it in mind, we can have a code that I will tell. The code is snow. Code is snow. That is from south to north. If the direction of current is from south to north, then the direction of the deflection of compass needle is towards the west. Understand? Similarly, from north to south, the deflection is towards the east. In such a way, you can identify the direction of deflection. Clear for you? Now, moving to the next term that we got from this experiment. What is the term? As we got a word that is magnetic field. Because this around this current carrying conductor, some sort of magnetic field is produced, and now we are able to define magnetic field. So what is magnetic field? You have studied electric field in the first chapter, because around the static charges there will be a region which exerts force on it. So that region around the charge is said to be what? Electric field. Similarly, in the case of magnet, there is a region around the magnet in which the force is experienced, okay, or that force is felt, and that region is known as magnetic field. Or in other words, you can say that around a current carrying conductor also there will be a region. Now you have seen because a current carrying conductor also behave like a magnet. So around a magnet or around a current carrying conductor, there is a region in which the force is experienced, and that region is known as magnetic field. Clear? This magnetic field is expressed by the letter B. Okay, these are all needed for our next topics. So magnetic field is expressed by the term B or the letter B. Okay. So you understood what is a magnetic field, and the letter used is B. Now the unit, the SI unit of magnetic field is Tesla. T. Okay. This is SI unit, and the CGS unit of magnetic field is Gauss. Clear? So 1 Tesla is equal to 10 raised to 4 Gauss. So this should be in mind because you have to solve the numericals. If it is given in Gauss, you have to convert it into Tesla. Okay. So these are the basic details regarding magnetic field. Now how to find the direction of magnetic field? You have studied one rule in your 10th standard, that is first one, right hand thumb rule. What is the rule? You are remembering? Right hand thumb rule. This is the first rule used to give the direction of magnetic field around a straight current carrying conductor. Okay. So if you are considering a straight current carrying conductor in such a way that, assume that the direction of current is along the thumb of your right hand. Okay, so in this way, direction of current is along the thumb. Then these curled fingers, okay, these 4 fingers will give you the direction of magnetic field around it. Understood? So for a straight conductor, if you closely observe, or by activities you have seen that for a straight conductor, what about the shape of the magnetic field? As it is concentric circles. For identifying the direction of magnetic field, we have studied magnetic field lines and all that you know. So the magnetic field lines are actually in circular shape, concentric circles. Understood? So these concentric circles will give you the direction of magnetic field. That is what given by right hand thumb rule. So if we hold a current carrying conductor, straight current carrying conductor in such a way that the direction of current is given by the thumb, then the curled or the wrapped fingers will give you the direction of magnetic field. Understand? So that's the right hand thumb rule. Suppose if you are considering like this. Okay, now you can see that in this way current is coming. Okay, so 2 points are there, right? So if here I am considering, you can see that it is inward. Here the magnetic field is inward, then it is coming like this, isn't it? So here if we want to know the direction, I will call it as inward, and inward can be represented as into mark. Okay, so here the magnetic field is inward. But when we speak about this side, no? What about this side? As the magnetic field is outward. Outward is denoted by dots. Okay, in some questions you will see like this, which means that the direction of magnetic field is into the plane of the board. Now if it is a dot, you will say that the direction is out from the plane of the board. That is what this into and dot indicate. So here in this side, if I am saying according to this rule, if this is my straight current carrying conductor and the fingers are going like this and turning around this straight conductor, right? So this side if I am considering, it is inward, and this side it is outward. Now how in the downward direction if I am taking, how? As I have to consider the current in downward direction, isn't it? So this will go like this. Am I right? Now here you can see it is going inward and here it is coming out. So in this case, in the downward direction of current, this side will be the inward portion for the magnetic field, and here it is outward. Clear? Now this way you can consider. This way you can consider. So this is the direction of the magnetic field, isn't it? This is the direction. So you can see here, come like this, isn't it? Come like this. Okay. Now in this way, if I am considering, this is the way. So here it is inward, and again down portion it is outward. Here it is inward and it is outward. So in any direction, if a question is coming, you can find by using the right hand thumb rule. Clear? So this is the right hand thumb rule. What is the purpose of this rule? As it is used to find the direction of magnetic field. I just want to mention that so many rules are there in this chapter, and each rule is for a special purpose. So maybe for a direction of force, or direction of current, or direction of magnetic field. So many things are there in this chapter. So first you have to identify for what purpose a rule is used, and then you have to study the concept clearly. Don't get confused with the rules, because so many rules are there. Later we will study a few more rules. Okay. So this rule is mainly to find the direction of magnetic field around a straight wire or straight current carrying conductor. Now the second case is for a closed loop carrying current. Okay, closed loop carrying current. In such a case, we will use another rule known as right hand screw rule. Right hand screw rule. This is for a closed loop carrying current. First case, right hand thumb rule is a straight current carrying conductor. Understood? Now if it is a closed loop, you have to consider the direction of current as the rotation of the screw, or the movement of the screw, in which direction we are moving the screw. That will give you the direction of current. Understood? Now the motion of the screw will give you the direction of magnetic field. I will make it clear. Suppose this is the screw. Okay. Now I want to pierce it here. So what will I do is I will turn it clockwise direction. This way I will turn it, right? So if I am turning it in this way, this screw will get fixed here. That means when I am rotating it in clockwise direction, what will happen? The screw is moving inward. Clear for you? So if the current is that is what the direction of current. That is, the direction of current is in clockwise direction, then the magnetic field will be inward. Clear? So direction of current in clockwise, magnetic, that means the screw will be moving in, isn't it? So the magnetic field will be inward. And if I am making it like this, that means I am rotating it anti-clockwise, the screw will get out from the wall. Clear? So what is the direction? It is outward. Clear for you? So direction of magnetic field will be outward when the direction of current is anti-clockwise. So if this is a loop, either the direction can be in this way or the direction can be in this way. If in this direction, we will call it as clockwise direction. So for a closed loop having clockwise direction, the current in the clockwise direction, what about the magnetic field? Yes, magnetic field is inward. Clear? Okay. Now second is in the anti-clockwise direction, the magnetic field is outward. Clear? Using that first right hand thumb rule also, we have stated the rule. How is this is straight current carrying conductor, magnetic field is given by the curled fingers. There also we mentioned the inward and outward from 2 points, isn't it? Now here it is closed loop in which the direction is clockwise or anti-clockwise. So at that point, if I am considering the magnetic field, either it can be inward, acting inward, or the magnetic field will be acting outward direction. Understood? So these are the two rules which we use here to identify the direction of magnetic field. Then next is You know, for a straight conductor, what about the shape of the magnetic field lines? Yes, they are concentric circles. For a straight wire, we will get concentric circles. You know that. Okay. Now, if this is the direction, you know, here in this way the current is coming. So, here the current enters and here the current comes out. Sorry, direction of magnetic field is outward direction. Clear? This is the direction of current. Now, the second case is for a circular loop. What about the direction? Circular loop, what about the shape of the magnetic field lines? This is the circular loop. So, at each point, if I am considering, I can take it as a single straight point, right? So, for this straight point, it will be concentric circles like this. At each point, it will start to continue. But as a whole, when we consider towards the center, if it is coming, it will be like straight lines. Understand? So, at the center of a circular loop carrying current, the magnetic field is very strong because from all the points like concentric circles are coming towards and it will turn into what? A circle. Understand? Sorry, turn into a straight line. So we can say that for a circular loop, what about the direction? As the direction or the shape of the magnetic field lines will be straight lines. For a closed circular loop. Understood? So these are the basic things that we notice here, and one more thing to keep in mind, that is this current and magnetic field are always perpendicular to each other. Current and magnetic direction of magnetic field are always perpendicular to each other because you know in the case of in the case of straight current carrying conductor, you are getting concentric circles. So if a particular point is taken, that point is perpendicular to the direction of current. So always current and magnetic field are perpendicular to each other. Okay, so these are the basic things that we want to study related to the direction of magnetic field. Now we are moving to one of the important law in this chapter, which is almost similar to the Coulomb's law in electrostatics, and the law is Biot-Savart's law. Biot-Savart's law, very important. Okay, so there is a question to compare this Biot-Savart's law in magnetism with the Coulomb's law in electrostatics. So actually this Biot-Savart's law gives the magnetic field at a point due to a current carrying straight wire. That is, if I am considering a wire like this, okay, so this is an infinitely long wire, so I have taken a bit of it, then let the name be XY. Here there is a point P at which I have to find the magnetic field. So magnetic field at this point P is given by Biot-Savart's law. So if I am understanding Biot-Savart's law, I can find the magnetic field at any point P near a straight current carrying conductor. You know, if it is a current carrying conductor, surely there will be magnetic force around it, which we call as the region magnetic field. So at this point P, it should have a value for magnetic field. What is the magnetic field experienced? So to find the value of magnetic field experienced at the point P near a straight conductor, this Biot-Savart's law is used. Okay, so first you have to understand the law, then we will move to its derivation part. Okay. So again, I am considering a straight conductor like this. This is an infinitely long conductor. Okay. Now in this straight XY conductor, I am taking a small piece which is having a length dl. So dl is a small element I have considered. Now current is passing, I is passing through the straight conductor, I is the current. Now this point P, I have to find the magnetic field. Now from this element dl, the distance to this P is taken as R. Okay, this much clear. Now this element can be called as the current element. So through this element current is passing. So this is the current element. In terms of current element, if dl is the element in which I amount of current is passing, means what is the total value here, as it is I dl. I dl. Clear for you? Now the angle between the line and this current carrying wire is taken as theta. Is much clear. Now, according to Biot-Savart's law, the magnetic field at a point near a current carrying wire is directly proportional to, that is, if it is a small element dl, the magnetic field experienced at this point can be taken as dB. Okay, so this dB is proportional to, first it is proportional to the current element I dl. Current element I dl, and secondly it is proportional to the sine of the angle theta. Sine of the angle theta between the current carrying wire and the line joining the element at the point P. Understand? Sine of the angle theta. Theta is the angle between the straight current carrying conductor and the line joining the point P towards the element. Understand? So it is sine theta. Then again it is inversely proportional to the square of the distance between them. That is the square of the distance. What is the distance from the point P to that dl element? So this is the law stated by Biot-Savart's law. So mathematically how can I write? That is dB proportional to I dl sine theta by r square. dB proportional to I dl sine theta by r square. This proportionality sign can be changed, and I can add a constant, and that constant is mu 0 by 4 pi. So dB is equal to mu 0 4 pi I dl sine theta by r square. This much clear now. Now here you can see this dl. dl is, I is not a vector quantity, but dl is a vector quantity. Okay, so dl is a vector. Also this is a position vector, right? So this r is also a vector. So keep it in mind. When we discuss the vector form, we need that. So dB is equal to mu 0 by 4 pi I dl sine theta by r square. Clear for you? Now what is this mu 0? Mu 0, you have studied epsilon 0 or epsilon naught as permittivity of free space in electrostatics. Now here in magnetism, this mu 0 is called the permeability of free space. Permeability of free space. Permeability means what? Suppose if there is a medium, okay, and if that medium, how much times that medium is able to spread the magnetic field in that medium. Okay, ഒരു മീഡിയത്തിൽ എത്രമാത്രം ആ മീഡിയത്തിന് എന്ത് ചെയ്യാം, മാഗ്നറ്റിക് ഫീൽഡിനെ അതിൽ സ്പ്രെഡ് ചെയ്യാൻ പറ്റും എന്നുള്ളതാണ് പെർമിയബിൾ എന്ന് പറയുന്നത്. പെർമിയബിലിറ്റിയുടെ വാല്യൂ കൂടുതലാണെങ്കിൽ മാഗ്നറ്റിക് ഫീൽഡ് അവിടെ കൂടുതലായിരിക്കും. ഓക്കെ, ചില മീഡിയത്തിൽ പെർമിയബിലിറ്റിയുടെ വാല്യൂ കുറവായിരിക്കാം, ചിലതിൽ കൂടുതലായിരിക്കാം. ഓക്കെ, mu 0 എന്ന് പറഞ്ഞാൽ എന്താണ്? പെർമിയബിലിറ്റി ഓഫ് ഫ്രീ സ്പേസ് ആണ്. ഓക്കെ, സോ mu 0 by 4 pi means there is a value that is 10 raised to minus 7. So what is mu 0? Mu 0 is equal to 4 pi into 10 raised to minus 7. This is the value for permeability. Permeability എന്ന് പറഞ്ഞാൽ എത്രമാത്രം ആ ഒരു പർട്ടിക്കുലർ സ്പേസിൽ ആ മാഗ്നറ്റിക് ഫീൽഡിനെ സ്പ്രെഡ് ചെയ്യാൻ പറ്റുന്നു എന്നുള്ളതാണ് ആ മീഡിയത്തിന്. ഓക്കെ, ഡിപ്പെൻഡിങ് അപ്പോൺ ദ മീഡിയം പെർമിയബിലിറ്റി വിൽ ചേഞ്ച്. നമ്മൾ എപ്സിലോൺ നോട്ടിൽ പറഞ്ഞ പോലെ അല്ലെങ്കിൽ എപ്സിലോൺ പറഞ്ഞ പോലെ, എപ്സിലോൺ മീൻസ് ഇറ്റ്സ് ദ പെർമിറ്റിവിറ്റി ഓഫ് എ പർട്ടിക്കുലർ മീഡിയം, ഇറ്റ് വിൽ ചേഞ്ച്, ബട്ട് എപ്സിലോൺ നോട്ട് ഹാസ് എ വാല്യൂ, റൈറ്റ്? അതുപോലെ തന്നെ ഇവിടെയും mu 0 മീൻസ് പെർമിയബിലിറ്റി ഓഫ് ഫ്രീ സ്പേസ് വിച്ച് ഹാസ് എ വാല്യൂ 4 pi into 10 raised to minus 7. Clear? Now this is the law, Biot-Savart's law. So how can you state the law? According to, similar to that Coulomb's law only. According to Biot-Savart's law, the magnetic field at a point near the straight current carrying wire is directly proportional to the current element. It is directly proportional to the angle theta between the line joining the point and the element, and also the current carrying wire. Then next is, it is inversely proportional to r square. You know that as the distance increases, what will happen? As magnetic field decreases. So it is inversely proportional to square of the distance. So dB is equal to mu 0 by 4 pi into ideal sine theta by r square, where mu 0 is the permeability of free space. Clear? Now you can find the unit of mu 0 and also the dimension of mu 0 the help of this equation. Okay, now if you are asked to write this particular equation in the vector form, how can you write in the vector form? So in the vector form, you know dB, okay, is equal to mu 0 by 4 pi, I is a scalar, dl is a vector, sine theta by r square. Here we are taking the magnitude only. Okay, dl. Now, if I want to change this into a vector, I have to multiply it with a unit vector, right? That is, unit vector will give the direction. So, r cap is equal to what? Vector r by modulus of r. Clear? So, if I change this value, mu 0 by 4 pi I dl sine theta r cap by r square into modulus of r cap. Clear now? So what is this? This is mu 0 by 4 pi I dl into r vector divided by r cube. Clear? Now you know here sine theta is also there. So this is like AB sine theta. Am I right? AB sine theta. And this AB sine theta you can write like A cross B. Okay. So in such a way you can change like DL cross R. Because DL R sine theta means AB sine theta. Understand? So DL cross R you can write. So this is the expression for the vector form of magnetic field. Now it is dB only. If you want to find the total magnetic field for that line element, what will you do? Is you will integrate. Such things you will discuss in between our coming sessions, because so many derivations are there. In such derivations we will discuss it clearly. Okay, so this is enough for the vector form. Okay for you. Now listen, here there are certain features for this Biot-Savart's law. First of all, I have to mention the feature, that is, it is analogous to Coulomb's law in electrostatics. So first one is analogous to Coulomb's law in electrostatics. Now the second one is, here in the from the equation it is clear that dB is perpendicular to I dl as well as r. Okay, dB is perpendicular to I dl, the current element, as well as the position vector. That is the second point. Now from the equation you have the expression dB is equal to mu 0 by 4 pi I dl sine theta by r square, isn't it? Now if theta is equal to 0 or 180 degree, what does it mean? As this dB is equal to 0. dB equal to 0, which indicates that in the line element itself you have to consider the point somewhere else. That is theta is equal to 0. So the value is minimum, no? dB equal to 0. And suppose if theta equal to 90 degree, dB is maximum. What is dB? Mu 0 I dl by 4 pi r square. So this is the maximum value for dB. Okay, in such a case, this point will lie exactly at 90 degree with this line element. Clear? So that's all about this, the features of Biot-Savart's law. Now there are certain differences as well as similarities between Coulomb's law and Biot-Savart's law. Okay. First of all, the similarity between this Coulomb's law and Biot-Savart's law, that from the equation itself it is clear for you. What is that? Yes, it is proportional to 1 by r square. Both E as well as V proportional to 1 by r square. That means it is a long range force, isn't it? Both are long range force. Okay. Now the second case, that's a dissimilarity, I would say. That is, electric field is produced by a scalar source. What is that source? Yes, it is electric charge, isn't it? But in the case of magnetic field, it is produced by a vector source, which we call as the current element IDL. So DL is a vector, IDL is a vector source. So this, because of this IDL, magnetic field is produced. And in the case of electrostatics or electric field, it is because of a scalar source, which we call as the charge. Okay. Now here in Biot-Savart's law, there is an angle dependence, isn't it? In Coulomb's law, we have the expression 1 by 4 pi epsilon naught Q1 Q2 by r square. But in Biot-Savart's law, we have the expression mu 0 by 4 pi into I dl sine theta by r square. So this, in this value, you can see that there is an angle dependence which is not present in where? In Coulomb's law. Okay. Now the fourth one is, in electrostatics, you have seen like Q1, Q2 charges, and the displacement vector is along the direction, isn't it? Along the direction, same direction only. That is parallel only. But in the case of magnetic field, actually the line element and the position vector are perpendicular, isn't it? So that is also a dissimilarity that we have to mention here. So that's all about the comparison between Biot-Savart's law and Coulomb's law. Okay. Now you have studied, now you are able to define permeability and permittivity. That is, permittivity is given by epsilon naught in free space and permeability is mu 0 in free space. So you have the value epsilon naught and mu naught. Clear? Now, in electromagnetic waves, you have derived one expression. Do you remember that? As C is equal to 1 by root of mu naught epsilon naught. This expression you have derived, right? So, how can you derive this expression here? That is what we are going to notice. So, we have first, we have to write mu 0 epsilon naught, mu 0 into epsilon naught. Now, I am multiplying and dividing this value by 4 pi, with 4 pi. Okay, so this will become mu 0 by 4 pi and epsilon 0, which is 4 pi epsilon 0. Clear? Now, what is this? Mu 0 by 4 pi is 10 raised to minus 7. 10 raised to minus 7. And 4 pi epsilon, 1 by 4 pi epsilon naught is 9 into 10 raised to 9. So, 4 pi epsilon naught is 1 by 9 into 10 raised to 9. Isn't it? That is 1 by 9 into 10 raised to minus 16. Am I right? That is what? If I am taking this here, 1 by 9 into 10 raised to 16, that I can write it as 1 by 3 into 10 raised to 8 the whole square, which is 1 by c square. Right? So here you got the expression mu 0 epsilon 0 equal to 1 by c square, or c square equal to mu 0 epsilon 0, or c is equal to 1 by, c square equal to 1 by mu 0 epsilon 0 and c equal to 1 by root of mu 0 epsilon 0. Clear for you? So this is the expression or relation between mu 0 and epsilon 0, that is permittivity and permeability. Clear? So today we have discussed Oersted experiment, then magnetic field, then how to find the direction of magnetic field for a straight wire as well as a closed loop. Then we move to Biot-Savart's law, derive the expressions, then comparison between Biot-Savart's law and Coulomb's law, then features of Biot-Savart's law, and finally moving to the relation between permittivity and permeability in free space with speed of light c, that is 3 into 10 raised to 8 meter per second. So that's all for today. Be thorough with this topic, because in the next class we'll be moving to the applications of Biot-Savart's law. So only those who understand this one can follow that class. Okay. So get ready for the next class. Thank you. Have a nice day.